we are having XAT is basically the analog signal. Here we are doing sampling at time t and we'll get this signal XANT. This is basically analog discrete time signal. Okay. And after doing A to D conversion, we'll get the actual digital signal. So this analog signal, we convert it into digital form by using A to D analog to digital converter here. Okay. Now in this process, this discrete time signals basically are the signals whose amplitude is defined at a discrete point in the time. Okay. Now t is basically the sampling time. Now here you can see here this is x of n, which is digital signal. This is analog discrete time signal. Now in this process you can see here t is lost. Okay, this a subscript is for analog. For digital I have not written anything. Now this nt, instead of nt it is only n, so t is lost here in this process. Now, in the sense that this n becomes a variable and it takes integer value. So this value n can be positive, can be negative, but they are integer. Now, each integer value in the corresponding discrete time corresponds to the integer multiplication of sampling intervals. So in this process, basically the T is lost in a digital signal. Okay. If a signal is derived from analog signal, T has to be kept in mind. Okay. Now in other ways, we can say that this T is normalized to the 1 second. Okay. Now, however, it's the beauty of this digital signal processing, or we can say discrete time signal processing, that the mathematical techniques to handle both these signals, that XANT and X of n, discrete time signal, and the digital signal are same. So basically we use difference equation, Z transform function, Z transform, Fourier transform. These techniques are there to handle these analog discrete time signal and the digital signal. So whether the dependent variable is continuous continuum like this XA and T, or a discrete amplitude, only amplitude like X of n, the techniques are basically the same. Okay, so these we can use interchangeably, XANT and the X of n. Okay, now in this case, this time t here, this t is sampling interval, and this we can define as t is nothing but 1 by fs, which is a sampling frequency. Okay, this fs is the sampling frequency. Now the signal processing is basically, digital signal processing is basically limited to half of the sampling frequency. We cannot go beyond half of the sampling frequency in a digital signal processing. Okay. Now, how to represent these digital signals? Now, basically, these digital now here you can say that this x of t is the analog continuous signal. Here we are having ADC, and here you will get the discrete signal, the digital signal like this. Okay, so we are having the amplitude values at the interval n. Now, how to represent this in a mathematical form? So we say that this digital signal, this signal is basically the sequence of numbers. Okay. Now this we basically represent with x of n. Okay. Now can be this n can be the values from minus infinity to infinity in the interval of 1. Okay, because n is the integer. Now in a symbol we can also show this sequence like x of n in curly bracket. Okay, for example, you can say here I'm having 0, 1, 2, 3, and here maybe some other values, and here I will show some arrow. This arrow represent the value at n equal to 0. Okay, this arrow you can give to any other values. Now this sequence says that I am having 0 value for n is equal to 0. For n is equal to 1, I am having 1 value like that. Okay. Now in this case, this values, now here I have written only the real values, but it is not necessary that all the values will be real. It can be a complex value. Okay. So there may be a signal like this. The sequence you will find like this also. -1 plus j, -2 minus 2j, like that. Okay. Now in this case, in the curly bracket you will find the values at different interval. Okay, like this. Now there are three ways to represent these signal, like time domain representation, the sequence notation, and the graphical representation. Okay, in time domain representation we can plot the plotting the signal amplitude versus the index n. In a sequence notation, just now I have said here, so this is basically the sequence notation. This is the mathematical notation to represent the sequence of values. Okay, like this. Okay, and graphical representation is basically plotting the signal values as points on a graph where x-axis represent the time index n and y-axis represent the signal amplitude. Okay, so this is the mathematical representation. For example, I'm having the digital sequence like this. Now in this case, arrow is here at 2. So at n is equal to 0, the value is 2. Okay. And like that, on the right side, it will goes like this is n equal to 1, n equal to 2, 3, 4, 5, like this. Okay. Now, if I want to show this a digital sequence in a graphical form, so I can show like this. So on the x-axis, I'm having x of the n, and on the y-axis, I'm having x of n. So at n equal to 0, I will show this is 2, magnitude is 2. At n equal to 1, I'm having magnitude 1. At 2, I'm having 3, like this I can show. Okay. Now the length of this sequence is also called as a size. Okay. The length of the signal is nothing but what? The length of the signal is nothing but the total number of samples in the sequence. Now, for in this example, I'm having how many samples? 1, 2, 3, 4, 5, 6. So I'm having 6 samples. Therefore, the length of the signal is basically having size 6. Okay, so this is represent with capital N. So capital N represent the size of the signal or sequence. So in this case, I am having N is equal to 6. Okay. Now, in this type of the discrete signal, I can say that there are uh, many types like even signal, even sequence, odd sequence, or the right side sequence or signal, left hand side sequence or signal. So periodic sequence or exponential sequence, like that, we will see the different types of the digital sequence, discrete signal. Okay, so we will see one by one. So the right side sequence, the right side sequence means what, or the right side signal is nothing but the signal where the values are non-zero on only for positive time indices. So in a graphical form, positive time indices means from n is equal to 0 on the right side. This is 1, 2, like this. So I'm having the non-zero values. So they may be having different magnitudes like this. So non-zero values only for the positive indices. Okay. So in other word, we can say that the signal starts after the index 0, and it can extend infinitely into the positive time domain along the positive direction. This is right side signal. In mathematical form, we can represent like this: x of n is equal to 0 for all n less than 0, and x of n is not 0 for all n greater than equal to 0. Okay, so the value is 0 for all negative time indices. The negative time indices means from n equal to -1 till minus infinity. Okay, so this is the right side signal. Similarly, the left side signal is what? So there will be non-zero values on the left hand side, -1, -2, like this. Okay, and all the zero values on the right side, on the positive indices. Okay, so mathematically I can say that the left hand side signal x of n is having non-zero values for n less than 0, and this is having 0 value for n greater than equal to 0. Okay, now even signal and odd signal, in the previous lecture also we have seen, but I will quickly revise this. Now the basically, the even signal is what? The even signal is the signal where the left hand side of this signal, left hand side means what? Basically, if I put this y axis along n is equal to 0, so this is basically the left hand side, and this is the right hand side. Okay, so in the even signal, the left hand side is equal to the right hand side. That means if the signal, even signal, I represent with xe of n. Now in this case, xe of n is equal to xe of minus n, then this signal is the even signal. Odd signal is what? Odd signal represent with the xo of n. Now, in the case of odd signal, please remember this thing. At n equal to 0, there will be a 0 value in case of odd signal. Okay. But for the even signal, this is not the case. You will find the finite value at n equal to 0 in case of even signal. Okay, so the odd signal is basically having the negative of the value at, that is xo of n is nothing but negative of value at xo of minus n. This is the odd sequence. Okay, now in general basically signal is neither be even nor it will be odd, but it is the combination. It can be anything, but you can decompose the given signal in even part and the odd part. Okay, now if I want to find out the even part of the signal, so signal basically represent in like x of n. This is the given signal. This can be anything. Now if the given signal I want to decompose in the even part, then this is the formula. Okay, so we can find out the even part. So it's very easy. You can just put n by minus n here. You have to add this x of n plus x of minus n divided by 2. Okay, so here the odd part is cancelled. Now if I want to find out the odd signal, in that case x of n minus of x of minus n. Now in this divide by 2, in this process basically the even part will be cancelled. This is how we can find the even and the odd signal, odd part of the signal. Okay. Now the other type of signal is the periodic signal or periodic sequence or periodic digital signal. Now here the signal x of n is said to be periodic if x of n plus x of n plus kn. If this holds, then we can say that the given signal is periodic, where this capital N is the positive integer. Okay, and this k will go from 0 to infinite. Okay, now this x of n basically repeats after every n samples. So we can say this is the periodic signal. So after every n sample, you can say here, so this n is having positive integer and k will vary from 0, 1, 2 like this. Okay, for k equal to 0, you can say x of n is equal to x of n. After the n positive integer, x of n is equal to x of n plus capital L. This is the next period. Okay. Now, the smallest n value, capital N value. So this smallest n for the validity of this relation is called the period of this signal. Okay. So in this case, in this digital signal, the period, this capital N, has no dimension. Therefore, it is not having dimension. It represents in the number. Okay, like in analog signal, how we represent the period in second or microsecond like this. But in case of digital signal, it is not there. There the signal is not having the period is not having any dimension. Okay, so it is in the number. Okay, so that means basically the period indicates the number of samples after which it repeats. Okay, that is there. Now, why the smallest value of n here? Why the smallest n? Now, suppose if we take example where I have considered n equal to 20. Now, this periodic signal will repeats. So, repetition will occur for n equal to 40, 60 like this, 80 like this, okay? But not for n equal to 10. But not for 10. Therefore, this is basically the smallest value. Okay, the period is basically the smallest value of n in the given signal. Okay, so this is about the periodic signal. Periodic signal. Okay, now the next type of the signal is the bounded signal or bounded sequence. Now, how to define this bounded sequence? So the definition is like this. So the sequence x of n is such that the magnitude of x of n is bounded. Now what is this bounded means? Now the magnitude of x of n, how we represent in the modulus mod. So mod of x of n is basically less than equal to some value m, and this value m is basically less than infinity. If this is less than infinity for all value of n, for all n, this is the symbol of for all n, okay? Now, then we can say that the x of n is bounded sequence, okay? So, the sequence x of n is said to be bounded when the mod or magnitude of this sequence x of n is less than equal to m. This value m is nothing but is less than infinity. Then in that case we say that this sequence, particular sequence, is bounded. Now again, there is a term like absolutely summable sequence. Now in this case, suppose I will add all the magnitude of this signal. Then if I do the summation of this magnitude, so from n equal to minus infinity to infinity, if this summation of all the magnitude, if it is less than equal to some value p, and this p is less than equal to infinity, then in that case I can say that this particular sequence is absolutely summable sequence. Okay. There is other term which is square summable sequence. Now square summable sequence, in this case we have to do the square of this magnitude. Okay. So from n equal to minus infinity to infinity, the square of the magnitude of x of n, if this summation is less than equal to some value q, which is less than infinite, then in that case I can say that this particular sequence is the square summable sequence. Okay. Now for example, the sequence is like this 1 by n. If the sequence is represents like this 1 by n. Now can you tell me whether this is the absolutely summable sequence or not? Now how we represent absolutely summable sequence? From n equal to minus infinity to infinity, 1 by n. Right, this x of n is nothing but 1 by n. I have directly written here. Now, this is minus infinity to infinity means you will come across n equal to 0. Now, at n equal to 0, that is 1 by 0, okay, which is nothing but infinite. Therefore, the summation of all this thing is not less than infinity. It is infinite. Therefore, this is not a absolutely summable sequence. This is not absolutely summable sequence. Now, can you tell me about this, whether this sequence is square summable or not? Is it square summable? Can you tell me
Yeah,
how
I
it is?
guess 1 over, since n is 1 over n, and if we square the n, even if there's 0, it still become 1.
No, but this is
No?
square of the magnitude of this. Okay. Now, again, square summable sequence, how you represent n equal to minus infinity to infinity, 1 by n square. Now, again, you will come across n equal to 0 here, right? So, if you put n equal to 0, then what you will get here? Infinite, infinite square. Again, it is not a square summable. Understood? Is it clear?
Yeah, doctor.
Yeah. Because we are doing summation over the signal. So this thing you have to check there. Okay. Now, this square summable sequence is also called as the finite energy sequence. If the sequence is square summable, then this is finite energy sequence. Okay. Now, for example, you can say that the square of a voltage with 1 ohm resistance, which is nothing but the energy you will get. Or you can say the square of current with 1 ohm resistor. This is also you will get the energy. Okay. So the square summable sequence is also the finite energy sequence. So this is used alternatively. Okay. Now, if I want to find the average power from the sequence, then basically the power is what? The power is nothing but the energy per unit time, right? Now, energy, we know that the energy is what? The summation of the square of this magnitude of the square of the signal. So, the energy is represent like this. Okay. So, I say that if n equal to minus k to k, this is capital K. If n goes from minus capital K to capital K, the summation of this sequence, the square of this sequence, is nothing but the energy. Now, the this is energy over what length? How to find the length of this? The length of this is basically what? This is equal, the length is 2k plus 1 because there is n equal to 0 in between. Therefore, the length is 2k plus 1. Okay. Now, the power is basically the energy per unit time. So, 1 by this length. So, I will do the 1 by the length of this signal. Okay. And if I limit this for k tends to infinite, then I will get the average power here. Okay, so this is basically what? This is basically the average power over length 2k plus 1. Okay, now if the signal is periodic, now this is the case when the signal is not periodic. Now if the signal is periodic, then in that case, how to find the average power? So it will be easy in the periodic signal case, because a periodic signal, if it is of length n, then you have to take average over only one period. Okay, because the every period indicates, because this will the next period will be the identical replica of the first period. So it will be simple in the case of the periodic signal. Okay. Now, how to represent it mathematically? So this you can say that if the signal is having period of n, so 1 by n summation from n equal to 0 to capital N minus 1 mod of x of n square. This is the average power in case of the periodic signal. Okay, this is the formula for the periodic signal to find average power in the periodic signal. Okay, now so in digital signal, basically we are having two elementary, most elementary signals. Okay, in the digital signal processing. So one is the impulse signal and the other one is the step signal. These are the most elementary signals. Okay, now if you compare, this is the representation of impulse signal in discrete form. This is the representation of step signal in the discrete form. So delta of n and u of n. Now, in case, if in the analog case, how we represent the signal, the impulse signal, we write delta of t, right? So if you compare with the analog impulse, that is delta of t, if you compare this delta of n with delta of t, it is quite complicated as compared to delta of n. This delta of t is complicated. Why? How delta of t we define? So we say that at t equal to 0, this is delta of t. So basically we say that delta of t exists at t equal to 0, and the amplitude at t equal to 0 is basically the infinitely large. So we are having infinitely large amount of amplitude at time t equal to 0. Therefore, it is complicated in case of analog representation delta of t. So we say that this delta of t from 0 minus to 0 plus dt, if we integrate this, we say that it is having the value 1. Okay. So energy over this, we say that it is having the unit energy. Now this creates basically the lot of problem. Okay, because this is not the function in the ordinary sense. This is unlimited function. Okay, this amplitude we cannot define. So therefore it is, we have taken the integral, that is the area over this. Okay. Now, in case of digital signal, if you say, so there is no such problem in case of digital signal, because how we represent the impulse signal in case of digital case? So we are having amplitude 1 at n equal to 0. This is very simple because delta n having amplitude 1 at n equal to 0, and it is 0 otherwise. Okay. Okay. Now the combination of this uh, impulse function give rise to the step signal. Okay. So basically this step signal is the combination of the impulse signal. Okay. So how we define the step signal? Step signal is basically having value 1 for n greater than or equal to 0. Otherwise, it is 0. So mathematically, how we write it? So mathematically, we say u of n is having value 1 for n greater than equal to 0, and it is 0 otherwise for n less than equal to 0. Okay. Now, this u of n we can represent in terms of delta of n. So how to represent u of n in terms of delta of n? Now, if I delay the unit impulse, this is unit impulse. If I delay this unit impulse by 1, so how will be the sequence? How will be the signal? So I will get 1, amplitude 1 at n equal to 1. Correct. If I delayed by 2, that is, this is basically what delta of n minus 1. How will be the delta of n minus 2? So this is nothing but at n equal to 2, you will be having amplitude 1. This is shifted towards the right. So this unit step signal is the summation of what? Summation of delta n minus k. Okay, and this k will vary from 0 to infinite. So if you add all these impulses, then what you will get? You will get the unit step signal here, this chain, right? Now this is vice versa. You can also represent this impulse signal in the form of step signal. So delta of n, if I want to find out in terms of this step signal u of n, so how I can write it? So this is simple. Delta of n is nothing but u of n minus u of n minus 1. Okay. U of n minus 1 is what? U of n minus 1 means this whole step signal is shifted towards the right. Means your step will be, your step signal will start at n equal to 1. Okay. So like this. So if you subtract this signal from this signal, what you will get? This single value, amplitude 1 at n equal to 0. Okay. So this is how we can write the impulse signal in terms of step signal in terms of the impulse signal. Okay. Now, for example, I am having this arbitrary sequence This is in the graphical form. So this sequence is having value 0 at n equal to 0, n equal to 1 having amplitude 1, n equal to 2 having amplitude 2, at 3 it is 3. So the size of this sample is basically capital N is nothing but the 4. Now, can we write these type of signal in terms of the impulse sequence and the step sequence? So yes, so we can write these in terms of the impulse sequence. So I say this is my signal x of n. So x of n is nothing but what delta n minus 1. At 0 it is 0, therefore it is not delta n. At 1 I am having delta value 1, therefore it is delta n minus 1. Now at n equal to 2 I am having amplitude 2, therefore twice of delta n minus 2. At 3 it is 3, therefore thrice of delta n minus 3. Correct? Because for unit impulse we are having only magnitude 1, but in this sequence it is magnitude 3, so you have to multiply it by 3, and summation of all these 3 is what? This signal. Okay, now how to represent this signal in the step sequence? So again we can represent this. Now here I'm having the sequence from n equal to 0 to n equal to 3, which is having the values. Okay. Now u of n minus u of n minus 4. So what it will give if you put n equal to 0 here? So what it is? N u of 0 minus u of 0 minus 4, that is minus 4. Minus 4 is not having any value, that means it is 0. Again it is having 0. So you will get 0 value here. Okay. Now the case, if you put n equal to 1 here, so if you put 1 here, so u of 1 minus u of minus 3. Again minus 3 is having value 0. So it is equal to u, the value equal to u of 1. So that is equal to 1 you will get. Now if you put n equal to 2 here, u of 2 minus u of minus 2. Again this is 0. But what is u of 2 here? U of 2 is nothing but having value only 1. Correct? So this you have to multiply by n. Then you will get magnitude 2 here. Okay, are you getting my point? Any difficulty? So like this we can represent the given sequence in terms of the step signal also. Correct? Now the other type of signal is or sequence is the exponential sequence. So the exponential sequence is also often used. So the sequence is in the form a into alpha of alpha to the power n. Okay, so if you start from n equal to 0, so it will goes like a a into alpha square, like this. Okay, now can you say that this type of sequence, exponential sequence, is bounded? Is it bounded? Because the general signal is represent with a into alpha to the power n. Is it bounded? How to find the signal is bounded or not? So we check the magnitude of the signal. right? If the magnitude is less than 1, in that case it is bounded. Okay. Now if this alpha is less than 1, in this case the right side of the signal is bounded. So alpha is less than 1 means what? If I consider alpha is equal to 0.5 in this case. Okay. The right side means the n equal to 0, 1, 2, 3. This is the right side. The left side means n equal to -1, -2 like this. Okay. So the right side means the a is some amplitude, the constant value. Suppose it is 1. So 0.5 to the power 1 is what? 1 by 2, which is less than 1. Then 0.5 to the power 2 is what? 1 by 4, which is again less than 1. Therefore, the right side of the signal is bounded. Right side of this signal is bounded. What about the left side? What about the left side? Left side means you have to put n equal to -1, -2, -3 like this. Now, for example, 0.5 to the power -1. This is what you will get here, value 2. Okay. Now 0.5 to the power -2 is what? Value 4. So it will increase indefinitely here towards the left side. One is having value 2, then 4, then maybe 8 like this. It will increase. So this signal is not bounded. Okay. But if you multiply this signal, if you convert this signal into the right hand side signal, how to convert this in the right hand side signal? So you can multiply this a alpha to the power n with u of n. Okay, u of n is what? Unit step. If you multiply with this given signal with u of n, then it is right sided signal. Okay, now you can say that this right sided signal is bounded. Okay, but it is bounded only for what? If your mod of alpha is less than 1, then it is bounded. If alpha is greater than 1, then it is, in this case, it is not bounded. Okay, because if you take alpha greater than 1, then it will again, you will get this signal like this, which is infinitely increasing towards the right. Okay. Now this alpha can be a complex value also. This can be real, negative, positive, can be complex. It can be anything. Okay. So this is about the exponential sequence. So what we have done here, we check for the boundness of the sequence, exponential sequence. Now the other type of signal is the sinusoidal signal. So most of the time we use the sinusoidal sequence. So the general form of this sinusoidal sequence is what? A into cos. This can be cos or cosine or sine. You can keep it. You can take anything. So A cos omega naught n plus phi, t or phi. Okay. This is the representation of the sinusoidal signal. A is the constant term. Okay. This is nothing but the frequency. Okay. Now, can you say that? can you check whether this signal is bounded or not? Is this sinusoidal sequence signal is bounded? So how we check the boundedness? We check the amplitude of the signal. So boundedness or bounded is basically referred to the amplitude. Now in this case, what is the amplitude of this sinusoidal signal? It is A, correct? Therefore, we can say that yes, this signal is bounded. Okay. Now, is this signal is periodic? So in case of the discrete form, it may be periodic, it may not be periodic. Okay. Now, if it is periodic means what? It should repeat after every period. So the case of periodic means what we say that x of n should be equal to x of n plus capital N. Then in that case, we can say that this is the periodic signal. So similarly, for this sinusoidal signal, if I take a equal to 1 here, cos of omega naught n plus phi, if it is equal to cos of omega naught n plus capital N plus phi, then in that case, here the omega naught n is basically what it is equal to 2 pi into r, and this r is nothing but the integer. Okay, so this omega naught capital N is basically the integer multiple of 2 pi. In that case, this is the periodic signal. Now, omega naught by 2 pi is what? R by N. R is integer, capital N is also integer. Okay. Now, in case of analog sinusoidal signals, basically all analog sinusoidal signals are periodic. But the digital sinusoidal signals may or may not be periodic. That you have to keep in mind. Okay. All analog sinusoidal signals are periodic, but we cannot say that all the digital sinusoidal signals are periodic. Okay, for example, suppose I'm having this sinusoidal signals, digital sinusoidal signal x1 and x2 and x3n, where the period for first signal is n1, which is having size 3, n2 for the second signal having size 5, and n3 is basically having 12. Okay, so all these three signals are the periodic signal. Okay, now if I say that the signal x4, which is the linear combination of these three signals, so if I multiply first signal by alpha 1, second by alpha beta and alpha beta and gamma, and if I add these, now whether this signal will be the periodic signal or not, so we can find out this. Now basically, if this is the linear combination of all the periodic signal, then yes, surely this signal is the periodic signal. Now what is the period of this signal in that case? If we add all these three signals, so suppose I say n4 is the period of this x4n. Now basically this n4, value of n4 is nothing but lowest common multiple of n1, n2, and n3. Okay. Now for our case, 3, 5, and 12, what is the lowest common multiple? So here the lowest common multiple is 60, right? So after 60 cycles, I can say that this x1 will execute 20 cycles. This x2 will execute how many cycles? 12 cycles. This x3 will execute 5 cycles, correct? Okay, so each of them must have completed integer number cycles. Okay, then we can say that this summation of all this digital periodic signal is also a periodic. Okay, so sum of all the digital periodic signal is also a periodic signal. Right. Now, here in this case, uh, if I want to go more in detail, in that case, so suppose I'm having the signal, analog signal cos of omega t plus phi. So I will do sampling over t and I will get a cos of omega n plus phi. Okay, and t here, capital T will come. And after A to D conversion, I will get actual digital signal cos of omega n plus phi. T will vanish here. Okay. Okay. Now in this case, the omega is nothing but what? This omega is nothing but okay. This omega n is nothing but what? This omega, I will say, is the omega in case of analog into the t, sampling time t. Now this t, how we represent? This is nothing but 1 by sampling frequency fs. Okay. Now this, again, this analog omega, I can say this is 2 pi into f divided by fs. Okay. So this is in radians and this is in hertz. Okay. Hertz is nothing but what? Cycles per second. Okay. So what you will get in final? 2 pi into f by fs. This is the omega, that is the frequency in case of the digital. This is analog frequency in case of analog signal. Okay, so I will say that this omega is dimensionless because this is f by fs we are getting here, so therefore it is dimensionless. Okay, however, this is dimensionless, but we represent this omega in radians, not in radians per second. This in case of analog signal, how we represent omega omega is basically the unit of omega is radians per second. Okay, But in case of digital signal, the frequency omega is dimensionless, but we express in terms of radians. Okay, not radians per second. It is only radians. Please keep in mind. Okay. Now this omega is what? This omega is nothing but this 2 pi f by fs. And in case of digital signal processing, we cannot go beyond 1 by 2 f of s. So you will get distortion if you go beyond this. Okay. So omega max, I will say this omega max is nothing but 2 pi fs by 2, because this is the maximum and this is fs. So the maximum allowable frequency is what? Fs by 2. So if you do this calculation, what you will get? This fs will cancel. You will get pi only. Okay, so the range of this digital, the range of this omega is basically from 0 to pi, you can say. Okay. So there must also exist a negative frequency. So in that case, you can say the range will vary from minus pi to pi. Okay, so this is basically the base signal. This is the base band, you can say. Okay. So the range of the region in the spectrum, the digital domain is basically from minus pi to pi. But the analog case, in case of analog, the frequency will vary from minus infinity to infinity. Okay, analog case, in that case, it is minus infinity to infinity. Frequencies will vary from this. But in case of digital, it is minus pi to pi only. So the whole range is now compressed to minus pi to pi. So it makes simple, right? Right. Now, this omega, you can also say that this is basically the normalized frequency. Okay, normalized frequency in radians. Okay. This is the extra thing I would like to highlight here. Now the operations we will see here, arithmetic operations of the on the sequences. Okay. So digital signals are basically subject to some operations. So operations like multiplication, addition, subtraction, division, like this. Okay. Now multiplication, suppose I'm having two signals like this, x1n and x2n. Okay. So I can multiply these two signals, two sequences. So how to multiply these two? So the corresponding samples are multiplied, right? Like x1 of 0 is multiplied with x1, x2 of 0. X1 of 2 is multiplied with x2 of 2, like this. So corresponding samples basically we multiply. Therefore, what is the multiplication of this 2? At n equal to 0, the value of x1 is 1. x2 is 1. Therefore, 1 into 1 is what? 1 into 1 is 1 here. For n equal to 1 here, it is 2, it is 2. Therefore, it is 4. For this case, it is what? It is 1 and 0. Therefore, it is 0. Now, you please understand here. Now, the size of this sequence is what? N1 is 3. This N2 is 4. If this the values are not given, in that case, you have to add zeros, because these two signals, two sequences are not having the same length, because this is having length 3, this is having length 4. If they are not having the same length, so in that case, you need to add the zeros here. Okay. So the value at n equal to 3 here, you have to say it is 0. Okay. So like that, you have to do the operations. Okay. Same for the addition. So addition means what? We have to take the corresponding samples. So we will add n equal to 0, x1, x2. So you will get what? This is 1 plus 1, 2. 2 plus 2 is 4. 1 plus 0 is 1 here. And this is 0 plus 1 is 1 here. So this is addition of this two signal. Same subtraction you can do, subtraction operation. Same you can do the division operation. Okay. Now, in case of the digital hardware, we cannot add more than two numbers at a time. So in digital, so in that case, suppose I want to add the three signals. So then I will need two summation blocks. So how to represent basically this in the mathematical, the description is what? So this is the multiplication sign. So I will say this is x1 of n, x2 of n, and I will get some output y of n here. Okay. So this is mathematically we can represent. For addition, we use summation block. Okay. For subtraction also we use summation block, but here you need to assign the sign. If it is x1 n minus x2 n, then you have to represent this minus sign here. Then you will get output y of n like this. Okay. If I want to multiply by scalar, in that case, if I want to multiply x1 of n by some scalar alpha, then in that case, in round bracket, you have to write alpha. Then it is alpha times x1 of n. Okay. Now the other operation, this is the simple operation, multiplication, this subtraction, addition, like this. The other operation is folding operation, or you can say the time reversal. Now, in this case, the given x of n is reversed to find x of minus n. This is reversed to find x of minus n. Okay. Now, if this signal is right side signal, then after time reversal or folding operation, what you will get? The left hand side signal. If the signal is left hand side, then you will get the right hand side signal like this. Now, for example, suppose I am having x of n like this. Okay. So you will see here after folding operation, the value at n equal to 0, it is 0. But value at n equal to minus 1, it will goes to n equal to 1. Plus 1 goes to minus 1. Plus 2 goes to minus 2. Plus 3 goes to minus 3, like this. So if it is purely right hand side signal, so after folding you will get left hand side signal. Okay, like this. For left hand side signal, you will get the right hand side signal like that. Okay, so this is the folding operation. Then delay operation. So how you will get the delay here? If there is a delay of nd samples in the signal x of n, so we represent this with this x of n minus nd. So basically, delay where we do the z inverse. This transformation basically we use for delay z transform. So if I'm having x of n signal here, so after this z transform, z inverse, there will be delay of 1 unit in the given signal. Okay, this is the one sample delay. Okay, now, so suppose I'm having the signal like this, x of n 0 1 2, I'm having 1 2 and 1. If there is a delay of 2 samples, then what, this will shift towards the right side, and after 2 samples it will start, like it is starting from n equal to 0, but after delay it will start from n equal to 2. Okay, so same sequence you will find after 2 samples. If there is an advance in this, advance of 2 means it will start in advance of 2 samples, therefore it will start from -2, and this same sequence will repeat here. Okay, so this is the delay operation. So if there is n number of delays in the system like this, so then in that case you need to add more z inverse. So there will be a chain of z inverse. Okay, suppose I want signal n minus capital N, so there will be n number of z inverse in the operation. So you cannot directly write z to the power minus capital N. Okay, do not write like this, but you have to add more number of z inverse here. Okay, so what is the z inverse function? So that we will see later uh, through in this course. Okay, so this is about the delay operation. Okay, so sampling theorem is okay. So the next part is basically the digital system. So till now what we have seen, so till now we have seen the digital signals. Okay. So what are the different types of digital signals are there? So the different properties of digital signals, different operations, what we can do on the signals, digital signal that we have seen. Okay, so the next topic is basically the digital systems. So I think for today we will stop here. In tomorrow's tutorial session, I will start with this digital system for about 15 to 20 minutes. We will finish this topic and then we'll do some numerical in tomorrow's tutorial session. Is it okay? So do you have any doubt in? Okay, so we will stop here today. ते का बरं आपलं नेट गेलं का?